Hi, in this session we are going to discuss Euler's equations of motion. We shall also have a brief discussion on force-free motion of a rigid body. In the last class we saw that under a rotation of the coordinate system, the component matrix of the moment of inertia tensor transforms according to this equation. And we can choose the rotation matrix in such a way that the transformed component matrix is a diagonal matrix. And these diagonal elements were called the components of the principal moment of inertia tensor. And importantly, once we choose the coordinate system in which the moment of inertia tensor is diagonal, the expressions for angular momentum and kinetic energy take simple forms. We saw that in such a coordinate system, the components of the angular momentum vector can be written in this form, L1 equal to I1 omega 1, etc. And the kinetic energy also takes a simple form, T is equal to half I1 omega 1 square plus half I2 omega 2 square plus half I3 omega 3 square, where I1, I2, I3 are the eigenvalues of the moment of inertia tensor. They are called the principal values. With that, let's move on to Euler's equations of motion. We start with what's known as the Charles's theorem, according to which any general displacement of a body can be represented by a translation plus a rotation. We shall not prove this theorem here, but we'll take it as our starting point. So according to this theorem, we can split the problem of rigid body motion into two separate phases, one involving only translational motion and the other only rotational motion. Now, if you are talking about a rigid body with one point fixed, right, there is only rotational motion about that fixed point, and there is no translation because one point is fixed. And for bodies without a fixed point, we can choose the center of mass as the reference point and talk about the motion of the rigid body as a translation of the center of mass plus a rotation about the center of mass. And it can be shown that the total kinetic energy and angular momentum split into one term relating to the translational motion of the center of mass and another involving rotation about the center of mass. So we can write T is equal to half mv square plus half I omega square. This is the kinetic energy corresponding to translation of the center of mass. M is the mass of the rigid body. And half I omega square is the kinetic energy of rotation. For many problems, such a division can be made for the potential energy also. And in such cases, the Lagrangian of the system would take a simple form, L equal to Lc plus Lb. The first part concerns the motion of the center of mass itself, and the second part concerns the rotational motion about the center of mass. Now, both in Newtonian and Lagrangian formulations, it's going to be convenient to use the coordinate system in which the moment of inertia tensor is diagonal, because then the kinetic energy can be written in this simple expression, T equal to half I1 omega 1 square plus half I2 omega 2 square plus half I3 omega 3 squared. Let's now focus on the rotational part of the motion alone. In such a case, the direct Newtonian approach leads to a set of equations known as Euler's equations of motion. Now we know that Newton's equations are valid only in an inertial frame. So first we choose an appropriate inertial frame, and then we can write down the equation of motion as dl vector by dt is equal to n vector. This is just the statement that the rate of change of angular momentum is equal to the external torque applied. The subscript here means that we are talking about an inertial frame. This equation is valid only in an inertial frame. So the time derivative here is with respect to axes that do not share the rotation of the body. We can now make use of this equation relating the time derivative of a vector in the space set of axes to the time derivative of that vector in the body set of axes. So according to this equation, the time derivative of some vector g in the space set of axes is equal to the time derivative of that vector in the body set of axes plus omega vector cross g vector. So using this, dl vector by dt in the space set of axes can be written as dl vector by dt in the body set of axes plus omega vector cross L vector. And with this, the equations of motion become dl vector by dt plus omega vector cross L vector is equal to n vector. Right? So we have dropped the b subscript here. because hereafter it's understood that we are talking about the derivative in the body set of axes. What we have here is a vector equation. So we can equate the components separately. We can write for the ith component dLi by dt plus the ith component of omega cross L is equal to the ith component of n vector. We can now make use of the result that the ith component of the cross product of two vectors can be written as epsilon ijk. Okay, so if you want to find the ith component of a vector cross b vector, for instance, we can write this as epsilon ijk aj bk. Sum over j and k is implied. Using this here, this equation becomes dLi by dt plus epsilon ijk omega j Lk is equal to Ni. That's the equation that we have here. We can now simplify further if the body axes are taken as the principal axis relative to the reference point, because then the angular momentum components are Li equal to II omega I. Remember, there is no sum over I in this expression. This simply means that L1 is equal to I1 omega 1, etc. Now the equation of motion we had was dLi by dt plus epsilon ijk omega j Lk is equal to Ni. Now we can substitute Li is equal to II omega I, and Lk here would be Ik omega k. And then the equations of motion can be written as d by dt of II omega I is equal to plus epsilon ijk omega j Ik omega k is equal to Ni. Here I are the principal moment of inertia and they are constants. So this equation becomes I d omega I by dt plus epsilon ijk omega j omega k Ik is equal to Ni. Remember, there's no sum over I here, but there's a sum over j and k in this term. So these are the equations of motion we obtained. The index I takes values 1, 2 and 3. So we have three equations here. Let's write them out. So for I equal to 1, this equation becomes I1 d omega 1 by dt plus epsilon 1 jk omega j omega k Ik is equal to N1. Here the first index of the Levi-Civita is fixed. Now we have to sum over both j and k. But in this summation, the non-zero values would be for j equal to 2, k equal to 3 and j equal to 3, k equal to 2. These are the only terms corresponding to a non-zero value for this Levi-Civita symbol, because the first index is already fixed and the value of the Levi-Civita is 0 if any two indices are the same. So carrying out this summation over j and k and retaining only the non-zero terms, this equation becomes I1 d omega 1 by dt plus epsilon 1 2 3 omega 1 omega 2 omega 3 I3 plus epsilon 1 3 2 omega 3 omega 2 I2 is equal to N1. All other terms in this summation are 0, okay, by the property of the Levi-Civita symbol. Now we see that epsilon 1, 2, 3 is equal to 1, whereas epsilon 1, 3, 2 equal to minus 1. So this equation becomes I1 d omega 1 by dt plus omega 2 omega 3 I3 minus omega 2 omega 3 I2 is equal to N1. Okay, so we can combine these two terms by taking omega 2 omega 3 outside and we get this equation I1 omega 1 dot, where omega 1 dot is d omega 1 by dt, okay, minus omega 2 omega 3 I2 minus I3 equal to N1. Okay, similarly, if you put I equal to 2 and do the same things, you would get I2 omega 2 dot minus omega 3 omega 1 I3 minus I1 equal to N2. Okay, and for I equal to 3, you would get I3 omega 3 dot minus omega 1 omega 2 I1 minus I2 is equal to N3. These equations of motion, either in this form or in this expanded out form, are called Euler's equations of motion for a rigid body with one point fixed. Let's now move on to a brief discussion of force-free motion of a rigid body. We are going to apply the Euler's equations to describe the motion of a rigid body which is not subject to any net forces or torques. Now, Euler's equations were three equations of this form. The first equation was I1 omega 1 dot minus I2 minus I3 omega 2 omega 3 equal to N1. Now, if the external torques are 0, we can set N1 equal to N2 equal to N3 equal to 0. The components of the torque are all 0. Okay, so the right hand side here becomes 0. The first Euler's equation becomes I1 omega 1 dot minus I2 minus I3 omega 2 omega 3 equal to 0. Okay, because the external torques are 0. Now this can be written as I1 omega 1 dot is equal to I2 minus I3 omega 2 omega 3. That's the equation we have here, and the other equations also follow in the same manner. We can write I2 omega 2 dot equal to I3 minus I1 omega 3 omega 1 and I3 omega 3 dot equal to I1 minus I2 omega 1 omega 2. Now if the rigid body is not subjected to any net forces or torques, then clearly its center of mass is either at rest or it moves with a uniform velocity. So we can always choose an inertial frame where the center of mass is at rest. The center of mass is stationary. And then we need to discuss only the rotational motion of the rigid body. And this is conveniently done if we choose a reference system whose origin is the center of mass, which is also the origin for the principal axis in the body. We saw that the Euler's equations take this form if the external torques and forces are 0. Now let's multiply the first equation here by omega 1 on both sides, the second one by omega 2 on both sides, and the third one by omega 3 on both sides, and add all these three equations. Okay, then we would get the left hand side would add up to half, no, there's no half, it is I1 omega 1 dot omega 1 plus I2 from here I2 omega 2 dot omega 2 plus I3 omega 3 dot omega 3. That would be the sum of the left terms in the left hand side, right? So this will be equal to the sum of the terms on the right hand side, which is equal to I2 minus I3 omega 1 omega 2 omega 3 is common in all these terms, right? So let's write it like this. This is equal to omega 1 omega 2 omega 3 multiplied by I2 minus I3 from here, okay, I3 minus I1 from here plus I3 minus I1 and I1 minus I2 from here. So that's plus I1 minus I2. Okay, but all these terms cancel because I2 is combined with minus I2 minus I3 adds minus I3 plus I3 is 0 and minus I1 plus I1 is also 0. So the right hand side is 0. All right. So the equation now we have now is this is equal to 0. Right. I1 omega 1 dot omega 1 plus I2 omega 2 dot omega 2 plus I3 omega 3 dot omega 3 is equal to 0. Okay. But we immediately see that the first term is the time derivative of half I1 omega 1 square. Similarly, the second term here is the time derivative of half I2 omega 2 squared. And the third term here is the time derivative of half I3 omega 3 squared, which means that this equation can be written as d by dt of half I1 omega 1 squared plus half I2 omega 2 squared plus half I3 omega 3 squared is equal to 0. So this equation says that the time derivative of something is equal to 0. We have identified a constant of motion. And we already know that the term appearing here is the total kinetic energy corresponding to rotation. So this equation means that the total rotational kinetic energy is a constant. So we can write T is equal to a constant. And this indeed is it is one of the first integrals of motion we can write down immediately for the case of torque-free motion of a rigid body. So we now have the principle of conservation of total rotational kinetic energy in the absence of external torque. Now let's look at the equation we started with. Dl vector by dt with respect to a space set of axes is equal to n vector. And if the external torques are 0, we have dl vector by dt is equal to 0, which means that L vector is also a constant of motion. L vector itself is written as L vector is equal to L1 I hat plus L2 j hat plus L3 k hat, where L1, L2 and L3 are components of the angular momentum vector. Now in the principal axis, L1 is I1 omega 1, L2 is I2 omega 2 and L3 is I3 omega 3, which means that L vector equal to I1 omega 1 I hat plus I2 omega 2 j hat plus I3 omega 3 k hat is equal to a constant. Okay? So we have another constant of motion representing the principle of conservation of angular momentum. We now have two first integrals of motion which can be solved in principle to describe the force-free motion of a rigid body. With that, I shall conclude. Thank you.